Financial markets generate millions of data points every second. Prices tick up and down, creating a chaotic stream of raw historical data. To make informed decisions, investment analysts must translate this historical price action into rigorous descriptive statistics. Every asset is evaluated across two primary statistical dimensions. The first is central tendency, which is used to define an asset's expected return. The second is dispersion, which is used to quantify the risk or uncertainty of that return. We are going to build the mathematical framework of portfolio analysis from first principles, moving from single asset risk to multi-asset diversification. Mastering these underlying mathematical foundations allows an investor to transition from observing volatility to actively managing it within a portfolio structure. We begin with central tendency, using the arithmetic mean to calculate a simple average. However, the arithmetic mean fails to accurately represent cumulative wealth when dealing with multi-year compounding returns. For a $10,000 investment earning 5%, 6%, and 5.5% over 3 years, a simple average suggests a return of 5.5%, but this is mathematically flawed for cumulative growth. Capturing the true compound annual growth rate requires the geometric mean. This formula takes the nth root of the multiplied multipliers for each period, rather than simply adding and dividing them. The geometric mean will always yield a slightly lower but more accurate result compared to the arithmetic mean. Geometric mathematics is mandatory for accurate portfolio projections. Relying on simple arithmetic creates a misleading view of total growth. Once we measure returns, we must quantify the uncertainty of those returns, known as dispersion. Simple metrics like range are easily distorted by extreme high or low outliers. To measure data spread around an average, we use variance. In this 10-year sample, the variance is 8.64. We calculate this by finding the difference between each return and the mean, squaring that difference, and averaging the sum. Because these numbers are squared, the resulting value is in different units than the original data, which makes it difficult to interpret. Standard deviation provides the solution. Taking the square root of the variance returns the metric to its original percentage format. This final number represents the baseline metric for isolated asset risk. Standard deviation summarizes historical volatility into a single percentage, showing exactly how much an asset's returns typically fluctuate. Standard deviation allows us to plot expected returns onto a theoretical normal frequency distribution curve. Statistically, approximately 68% of all returns will fall within one standard deviation of the mean, and 95% within 2 standard deviations. In reality, long-run equity returns do not perfectly conform to this symmetrical pattern. Equity markets exhibit kurtosis. They are skewed, producing extreme positive and negative returns more frequently than a bell curve predicts. Many financial models fail to account for these massive, infrequent data skews. While the normal distribution serves as a theoretical benchmark, ignoring kurtosis leaves investors exposed to severe market shocks like the global financial crisis. Holding a single asset in isolation leaves an investor exposed to 100% of its individual standard deviation. True diversification combines assets so that the portfolio's total volatility is lower than the weighted average sum of its individual parts. This is achieved by measuring correlation, how the returns from two different assets move together over time. On a scale of -1 to +1, a 0 indicates no predictable relationship between two assets. Covariance is the statistical measure that synthesizes individual standard deviations with their correlation coefficient. When assets have a negative covariance, their opposing price movements cancel out, reducing overall portfolio volatility. An asset with a high individual standard deviation can be beneficial to a portfolio if it has low or negative correlation with existing holdings. By assembling assets based on negative covariance, investors suppress total portfolio volatility more effectively than by selecting low-risk assets in isolation. Investment professionals prioritize the optimization of the return-to-risk ratio over raw performance maximization. They seek the highest possible geometric return achievable for a specific level of portfolio covariance. This process relies on the accurate measurement of compound growth, the quantification of isolated risk, and the identification of negative correlation. It is important to recognize that correlation coefficients are highly dynamic and can change rapidly. During periods of market stress, investors often see a phenomenon known as correlation compression. In extreme events like COVID-19, nervous investors liquidate risky positions simultaneously, causing correlations to spike toward +1 and removing the benefits of diversification. Rigorous analysts understand that statistics represent probabilities, not guarantees, and effective management requires constant adaptation.